What's the first thing one does when they inherit a full complement of machine tools? You would think the answer is to make something, but you would be wrong. These machines have not seen regular use in close to a decade, and in my grandfather's later years, he was not able to maintain them as well as he used to. So as much as I want to get straight into making something, this equipment needs some serious TLC. Yes, I did fire these bad boys up to get an idea of what worked and what needed repairs, and I even made a few chips. Since these machines have always been in my grandfather's hobby shop, they were never exposed to the elements, nor did they ever see seriously high use like in a production environment. So the rust and wear is not egregious enough to warrant a full teardown. At least that's what I'm hoping, fingers crossed. As I reveal the true condition of things underneath the dust, grease, and rust, I'll be assessing the machine for other maintenance concerns and correcting them along the way. The grease and dust doesn't exactly hurt the machine, and I'm sure after just a few months of running, they'll look just as bad again. But you know, new shop, new to me machines, there's something just not right about leaving them in this state. So let's get started. I'll be starting with the mill, and my general approach is to start at the top and work my way down. A first pass with a wire brush knocks away all the loose dust and works especially well for reaching into the nooks and crannies too small for my big dopey fingers. With most of the loose dirt gone, I'm using a general degreaser to wipe down all the visible surfaces. This gets a good amount of the grime off, but when the degreaser doesn't do the trick, a Scotch-Brite pad with cleaning solvent from the parts washer can usually get the rest. Most of the unpainted areas showed signs of rust, and while not all of them are precision surfaces, I still wanted them to look nice. I soaked the shop towel in liquid rust converter and then held it to the rusty surfaces in saran wrap to prevent it from drying. After a few hours, the rust came right off, leaving a nice metal surface underneath. I'm not convinced this worked any better than mechanically scrubbing with Scotch-Brite, but it did free me up to clean other areas while it did its thing. Since I'm working through the top half of the mill, it's as good a time as any to get reacquainted with all the doodads going on up here. As a whole, this section of the mill is called the head. This mill actually has two. Why? I'm not exactly sure. The head controls the cutting bit, and that's really where all the magic happens. So I want to pay extra attention to make sure everything is in proper working order. This all starts off with a constant speed electric motor, which feeds into a continuously variable transmission, or CVT, and that powers a spindle, which holds the cutting bit. The transmission is critical to setting the cutting bit at an appropriate speed for the operation being done. The CVT has an infinite number of speeds, but only within a certain range. That's why this mill has a back gear. The back gear lets you choose between high and low gear, giving you a range of faster or slower spindle speeds. Forward is high, backward is low, and middle is neutral. So, what is the spindle? This is the spindle. It runs from where the cutting tool mounts all the way up through the transmission. I would show you this, but that would be a lot of disassembly and everything seems to be running fine here, so you'll have to take my word for it. Through the middle of the spindle is a long bolt called a drawbar, and that secures the cutting tool to the spindle. The head of the drawbar is at the top of the transmission, and you use a wrench to thread and unthread it from the cutting tool. The mounting end of the spindle actually has a special feature on it called a R8 locking taper. It's called locking because it does exactly that. Just lightly press the tool into the spindle and they lock together. Fully tighten it with the drawbar, and this tapered interface is strong enough to transmit all the torque of the cutting forces. The last feature of the head is the quill, and you'll need to bear with me for a moment because this is the absolute coolest part of the mill and I can't talk about it without geeking out. The quill moves up and down in the head and it houses the spindle, kind of like a drill press. The long handle to the right is the manual quill feed lever, and this is the quill lock, which should be pretty self-explanatory. While these are nice features, there are a few things about this mill's quill that make it a little bit cooler than your regular old drill press. First is a micrometer adjustment nut. If we want to limit how far down the quill travels and thus limit the depth of our cut, The micrometer nut serves as a hard stop for that depth. Perhaps even cooler than that, the coil has a power feed for driving the spindle down automatically. Simply engage the automatic feed with this crank, adjust your feed rate with this selector, set the feed direction with this knob, and finally pull the feed control lever. But the absolute best part about all this, once you hit your set depth, it automatically disengages the feed and the coil shoots back up. So you can set this machine to run, let it go, and it'll stop all by itself. I hope you're as impressed with this as I am. Enough playing around. We're here for maintenance after all. As you just saw, everything up here seems to be running well, so a quick wipe down and a spot lubrication of a few parts and I think we can move on. The head is attached to the rest of the mill through a series of adjustable axes, ending in the largest part of the mill called the column. The column is a single iron casting and serves as the foundation for mounting everything else. Atop the column sits the turret, which can spin around 360 degrees, and then stretched across this is the ram, which can move in and out. These can be useful for reaching far out on setups and giving extra travel clearance to the table below, but in general should remain relatively close and square to the column. As for maintenance in these areas, there isn't much to do. Loosening the locking bolts and verifying everything moves freely is basically it. The cleaning, on the other hand, is a lot more interesting. With the column of the mill extending down under the rest of the machine, it catches the majority of the metal chips, oil, and coolant. Mix it all together and let it sit for a couple decades and it makes a nice sludge that's super satisfying to scrape off with a putty knife. It also takes half a box of shop towels to clean up. The last little bit between the head and the ram is called the head-ram adapter. This front head has two axes for tilting the head left and right as well as forward and backward. This means the front head can be set exactly perpendicular to the working table, which is critical if you want your parts to come out flat and square. These adjustment axes in the turret, ram, and ram adapter should only be considered as setup axes. I say this for two reasons. First is that even though some of these axes have scales on them, these are not precise enough for making cuts. These scales are really only there for a reference to get you close to your setup. Second is that the movement of these axes is not smooth, like at all. When the locking nuts for these axes are loose, the joints become pretty unstable and the action is jumpy. No way could you make a nice cut with that kind of motion. That's what the cutting axes are for. This mill has three. X for left and right, Y for in and out, and Z for up and down. The movement of these three axes are much smoother and more precise than the setup axes. The precision mainly comes from three components. The first of these is the knee. The knee connects to the column and rides along these smooth metal surfaces called ways. These are called dovetail ways, and because of their shape prevent movement in both the left, right, and the front-back direction. The top surface of the knee is precision ground at a 90-degree angle to the column side, making up another set of ways that a component called the saddle rides along. The saddle straddles the top of the knee and has a matching set of what are called boxways on its underside, making up the Y-axis. The top surface has yet another set of dovetail ways that holds the table, making up the final movement axis, the X. The condition of the ways directly translates to the quality of the cuts, so my main objective here is to make sure they are damage, rust, and grime-free. Lucky for me, these ways have always had covers on them, so they were mostly protected. Just a general wipe down and some very light de-rusting got these ways looking and feeling their finest. Now just because the ways on the knee, saddle, and table are precision ground doesn't mean the precision is guaranteed. There is still a lot of play in these ways. You probably can't see it on camera, but you can definitely hear it. Mounting a dial test indicator reveals the truth. That's over 20 thousandths of an inch of play, and that's just one of the axes. Fortunately, each of these ways has something called a gib. You can think of this gib like a shim that is tapered along its length. The farther in the gib is inserted, the less play there will be. So each way has a special screw for positioning the gib, letting me set the play as low as possible without locking everything together. Since I have to adjust each of the 3 gibs, I went ahead and pulled them out entirely so I could get all the metal chips and grime out that could throw off the adjustments and generally gum up the works. While there is still some play, it is way less than before. Ultimately, these adjustments are a compromise between the amount of play and how hard it is to turn the hand wheels, so I'll just have to live with this. Speaking of hand wheels, let's address these while we're down here on the floor. The hand wheels on the knee, saddle, and table each drive threaded shafts called lead screws. The shape of the lead screw threads is actually trapezoidal rather than triangular. This not only makes them more precise, but also a bit easier to turn under load. Each of the lead screws has a position dial mounted to it, but like most of the mill, there is some play in the threads. This is called backlash and makes the hand wheel dials inaccurate. Fortunately, I have the backlash cheat code. These are called linear encoders, which are basically digital measuring tapes, but way more accurate. Connect these linear encoders to a digital readout, or DRO, and this system will display the real-time position of the table and saddle down to 0.5 of an inch. Since this is literally reading the position of one part relative to the other, the backlash becomes a non-issue. Now up to this point I've introduced a lot of moving parts. We have spindles and quills and ways and gibs and lead screws, and guess what? All of these need lubrication, or before long this thing will be the world's largest paperweight. Even trickier, some of the spots that need oil aren't super accessible. Thankfully, the designers of this machine has a solution or two for this. Lubricating the spindle and quill is pretty straightforward. On the head there are these 2 tiny oil reservoirs. Topping these off at the beginning of each use will prevent the spindle from exploding in my face. The oil pumping system for the axis ways and lead screws is far more elaborate. Starting off there is a reservoir that holds oil for the ways. The oil flows through passages drilled directly in the castings and is deposited right at the metal-on-metal interface of the ways. To prevent metal chips and dirt from getting at these interfaces, flexible scrapers wipe the surfaces, keeping them clean. And just as an extra layer of protection, rubber way covers prevent metal chips from settling on the ways in the first place. But even with all this protection, grime will always find a way. So part of my routine will be to keep these ways as clean as possible. A mill's precision is only as good as its setup. With everything clean, lubricated, and running smoothly, the last thing to do is dial it all in. The first step is to set the mill head square to the table. This process is called tramming and takes a bit of patience and a light touch. To start, I've mounted a dial test indicator with a special clamp to the spindle so I can swing it around 360 degrees. I ran a whetstone over the table surface to knock down any high spots. Then I placed the gauge bar across the table and raised the knee up until I started to read on the indicator. Swinging it around, I can't even get the indicator up on the bar. That means the head is tilted too far to this side. Loosening the 4 bolts on the front of the head lets me adjust the tilt incrementally while swinging the dial indicator back and forth. When I get similar readings on each side, I know I'm getting close and move on to the forward tilt axis. I did the same operations with the gauge bar aligned front to back, loosening and adjusting this axis. Once I start to get equal measurements in both positions, I can slowly start snugging up the locking bolts. But each crank on the bolts made the adjustments shift by a little bit. This part really takes patience. After several minutes of switching back and forth between the 2 axes, I feel pretty good about my alignment. At all 4 positions, I can get the dial indicator to read within 1 tick mark. To my delight, I realize this dial indicator is actually showing 0.1 of an inch, which means this table is pretty damn square to the spindle, and the gib play is way better than I thought it was. With the head trammed in, I just have one last step of aligning the vise. With an equally creative indicator setup mounted to the head, I can adjust the angle of the vise with some light taps of a hammer until the reading is dead constant across the fixed jaw of the vise. Snug up the locking bolts, make sure nothing moved, and I think that's it. It's done. The mill is done. Now I can start work on the lathe. I lied. I can't do all that work and not make some chips. Let's see what this bad boy can do. Look at that, a perfectly square block. Or whatever. Glad I got that out of my system. I do have a real project in mind that will need the mill, but it will also require the lathe. And well, just look at it. I guess I should do something about this first. See you next time, and thanks for watching.